as you recall from yesterday, right, we're talking about perturbation theory. That is the systematic way to get approximate solutions for problems that are close to exactly solvable problems, but a little bit different. And so the idea is that we want to make a power series with powers of the difference, assuming it's some small difference. Okay. So, we were in the middle of doing this big calculation yesterday. So I'm going to refresh your memory about where we are and then continue on and finish it up. Okay. So the idea is, right, there are math problems like, calculating e to the small number, right? Or physics problems like finding the energy eigenvalues and eigenstates for this particle in a box with a little bump down here. Those are the things we're going to work on. Okay. So for the math problem, there's this well-established procedure that you've seen in math classes by of making a Taylor series, so that if you know a function at a particular place x0, and you want to know what is the function at a nearby place x, you can make a series like this, that f of x is a 0th order term plus a 1st order term, a 2nd order term, a 3rd order term, etc. Right? And then assuming that x is really close to x0, all of these terms are getting smaller and smaller, right? And so if you want, a rough approximation, you could just do the 0th order, or maybe 0th and 1st, right? If you want a better approximation and you're willing to work harder, you can put in more and more terms. Okay, so that works for the math problem. Okay, and in this math problem, we have kind of an automatic procedure for making the series. That is, the Taylor series formula tells you how to make a series, right? So it tells you how to construct each of the terms here. Okay. Now we're going to do the same kind of thing for a quantum mechanics problem. But now we have to do it in sort of a manual way. That is, we want to find a series for the energy eigenvalues and the eigenstates psi of some problem, okay? But we don't have anything like the Taylor series formula, so we have to figure it out, okay? So to figure it out, we're going to say for the energy eigenvalues, it should be that there's a 0th order term. It's the eigenvalue for the unperturbed problem, the exactly solvable problem, and then plus our small parameter lambda times a 1st order term, and a lambda squared times a 2nd order term, et cetera, et cetera, et cetera. Right? And the same thing for the eigenstates, that each of the eigenstates should be the old unperturbed eigenstate of the exactly solvable problem, plus a 1st order correction, plus a 2nd order correction, et cetera, et cetera, et cetera. So now we know what are the 0th order terms, right? These go along with our exactly solvable state. Okay? So we want to figure out what are the 1st order terms and maybe the 2nd order terms. In order to do that, we set up the time-independent Schrodinger equation. That is the eigenvalue equation. It's the Hamiltonian acting on the eigenstate equals the energy eigenvalue times the eigenstate. All right. Now, everything in this equation can be expressed as a power series in powers of our small parameter lambda. Okay? So the Hamiltonian is like this, right? 0th order plus 1st order. Here's the eigenstate. That equals the energy eigenvalue times the eigenstate. Okay? So now we're going to multiply all this stuff out and express everything in powers of lambda. Okay, that lambda lets us organize everything on both sides of the equation. Okay, so here it is, where the terms circled in red are the 0th order terms. The terms circled in blue are the 1st order terms. The terms circled in green are the 2nd order terms. And that's as far as I'm going to go. Okay. So the 0th order stuff, this has to be equal term by term. Okay, so 0th order has to equal 0th order. That's already automatically true, because that's just showing you what's the original unperturbed problem. Okay, so no trouble with that. Okay, what about the 1st order terms? Okay, so if we want to set blue equals blue on the two sides of that equation. Okay, that's what we did towards the end of the last class. All right, so we can cancel the factors of lambda. And then we have this pair of terms equals this pair of terms. What can we do with that, right? Well, for one thing, we can take the inner product of both sides with this bra, the psi 0n bra. Right? When we do that, we see that the first term here cancels the 1st term there. And then the inner product here is 1. So look, we get a nice equation for the 1st order term in the energy eigenvalue. This is the 1st order correction to the energy value E sub n. Okay, and look at what it is. It is an expectation value, right? This is an expectation value where you take the perturbation, that is, you take the little change in the Hamiltonian, and you find what is the expectation value of that operator in the old unperturbed state, okay, the state psi 0n. So that is a relatively simple thing to calculate. That is, if you know what are the old unperturbed states, okay, you just need to make up an inner product where the perturbation H prime acts on the old ket, and you take the inner product with the old bra, and you're done. Okay, so we did an example of that for this kind of a bump in the particle in a box. Okay, so the perturbation is this little increase in the potential energy on the left side of the box. And we put that into the old unperturbed state, and we got this change in the energy, right? So we get the expectation value, which we calculate, you know, like we've been doing expectation values all semester. All right? And that gives us the change in the energy for state number n. Okay, this is the 1st order change. Okay? In general, that might depend on n, but in this particular problem, it doesn't. It's the same energy change for each of the states. okay? So that means for each value of n, 1, 2, 3, right? There's the old energy, the 0th order term, and then there's the new energy with the perturbation. That's the old energy plus the first order correction. So old plus first order, or 0th order plus first order, 0th order plus first order. Okay, so this is now part of the problem that we set out to solve. Okay, so if we go back to this plan for what we're trying to do, okay, we already knew the 0th order terms. We now have this first order term for the energy. Okay. Now, what's next, right? Well, we might want to know what's the change in the wave function. Okay, so that would be the first order term for the wave function. We might also want to go to second order to say, for example, what's the second order change in the energy eigenvalue? Okay, so let's do those things now. Okay, that's the calculation I want to show you now. Okay, so this is one of those relatively long derivations that I need to show you, okay? And so this, you know, it's probably good for you to see it at least once, so I'll do it now. But for those of you who can't stand long derivations, you can just click on fast forward to go forwards to the end. And I sure wish I could do that, but I can't. Let's see how we can do it. Okay, so you remember we are trying to solve this set of equations here where 0th order equals 0th order, first order equals first order, second order equals second order, right? So red equals red, blue equals blue, green equals green. Red equals red, done, no problem. Blue equals blue, right? Well, we partly solved it, right? I mean, here's the equation for blue equals blue. We took the inner product of both sides with this product. And so now, you know, the inner product of the left equals the inner product of the right, okay? That is necessary, but not sufficient, okay? So we still can try to extract more information from this equation, this blue equals blue equation. So let's work on this a little bit more to see what we can say about the first order change in the wave function, because the wave function is sitting right here. This is the first order change in the wave function over there and over there. Okay, so let's see how we can get out information about it. Okay, so I'm going to copy and paste this equation and work on it some more. Let's see, okay. Copy. All right, now I'll go way to the end. Paste. All right. So we have this equation, and we canceled the lambda factors. Okay, so now what can we do with this? Okay, well, what I really want is to find out information about the change in the wave function. That is this guy and this guy. So let's take the stuff I want to solve for, and I'll put it all on the left side of the equation, and all the other terms I'll put on the right side. Okay, so to get the psi1 stuff on the left side of the equation, okay, so that is the old Hamiltonian H0 acting on psi 1 n minus E 0 sub n times psi 1 n. Okay? And that has to be equal to the other stuff, okay? So equal to negative H prime, the perturbation in the Hamiltonian, acting on psi 0 n. Well, here, let me move that over. H prime acting on psi 0 n. And then there's this other term right here. So the E1n times psi 0 n. So minus E1n times psi 0 n. Okay, so now we can say in this equation, what is known and what is unknown. Okay, so we know the old unperturbed wave functions. Okay, we know what's the perturbation in the Hamiltonian. Okay? We now know what's the first order change in the energy eigenvalue, right? That's what we found yesterday. Okay. We know the unperturbed Hamiltonian. We know the unperturbed energy eigenvalues. Okay, so these are all things that we know. Okay, what we don't know, what we want to find is this guy. That is, what is the change in the energy eigenfunctions? Okay. So how can we solve to find this thing, right? Well, the trick is that we can express this function as a sum of the old energy eigenstates, okay? How do I know that? Well, because we can express anything, any function as a sum of the old energy eigenstates, right? The old energy eigenstates are a basis for Hilbert space. We can express any vector in Hilbert space as a sum of those basis vectors. Right? So this unknown thing, whatever it is, we can express it as a linear combination of the unperturbed psi n states. Okay? It's the same way that if you have a vector in 3 dimensions, an unknown vector in 3 dimensions, you can express it as something times x hat plus something times y hat plus something times z hat, right? Any old vector can be written that way in 3 dimensions. So here's the same thing, but for quantum mechanical states, which are vectors in Hilbert space. Okay, so if we want to do that, we could say psi 1 number n. It should be a sum over these psi zeros with some coefficient. Okay, so now we have to label it, right? Well, n is some fixed index, right? So if I'm looking at a particular value of n, like number 13, n equals 13. So this has to be a sum over, well, I'm not going to reuse the letter n, I'll call it something different, like m. Okay, so a sum of some coefficient sub m times psi 0 sub m summed over m. Okay. Now, the coefficient that goes here, that'll depend whether you're looking at expressing, psi 1 for n equals 12 or n equals 13 or n equals 14. So it better have a label n on it also. Okay. Does this look good so far? All right, that we're just going to express it in terms of the basis. All right, and then our equation becomes H0 minus E0n acting on this sum C nm psi 0m is equal to this thing, minus h prime minus E1n acting on psi 0n. Okay, now one reason why this is a good thing to do is that we know what the old Hamiltonian does to the old energy eigenstates, right? That it produces an old energy times the old energy eigenstate. Okay, let me write that out. I think maybe I shouldn't skip steps. Okay, so let's write that out. All right, I'm going to copy and paste this onto the next slide. Copy, paste. Okay, so if I want to write all this out, okay, so this is now going to be the sum over m. Okay. In this sum, we have the coefficient CNM, okay, and then that is multiplying H0 acting on psi 0m minus E0n times psi 0m. Okay. And this equals the same thing on the right. Okay, now what? Now we know what is this. That's what I was trying to say a minute ago. Okay, we know that the old Hamiltonian H0 acting on the old psi 0m equals the old energy m times the old psi 0m. Okay, so now we can simplify what's on the right side, the left side a little bit more. This turns into a sum of this coefficient times E0m minus E0n times the wave function psi 0 equals minus h prime minus E1 n times psi 0. Okay, so now how can we work with this, right? Well, the trick again is to take an inner product of both sides. Okay. So let's take the inner product of both sides with a bra corresponding to, well, any of the size, the old unperturbed size, like size 0L. Okay, what happens here? On the left side, we have sum over M, C, N, M, E0M minus E0N. Okay, and then there's this inner product of this bra psi 0L with the ket psi 0M. Okay, this is equal to, what's it equal to? What is it equal to? It's equal to, well, we have an inner product of psi 0L acting on the operator H prime acting on psi 0N plus E1N, and then there's this inner product of psi 0L with psi 0N. And now, finally, this actually simplifies a little bit. It simplifies a little bit because this is an inner product of one of the old eigenstates with another old eigenstate, okay? And those things are assumed to be orthonormal, okay? So that inner product is delta Ln. And likewise, over on this side, this is delta Lm. Okay, so now we can do the sum on the left side, right? This is a sum over the index M, but one of the factors in here is this Kronecker delta. So you know the story, we've been doing it all semester, right? When you have a sum like that, only one term in the sum is non-zero. That's when M equals L. All the other terms in the sum are zero, okay? So we only need to write down in the sum, what's the M equals L term? Okay, so let's do that. Here, I better copy and paste again, otherwise I'm gonna forget something. All right, way up here. Okay, so on the left side, we have just the term with M equals L. So it is C superscript N subscript L times E0 L minus E0 N. That's it. Okay. And then on the right side, we have this inner product, psi 0L, H prime, psi 0N, plus E1N delta Ln. Okay, so let's check out now what is known and unknown in this equation. Okay, so we already know this energy change, right? This is what we found yesterday. Okay. This is a matrix element, right? It's the matrix element of H prime between the states L and N, the old unperturbed eigenstates. So this is also something that we know, or we could do an integral to find it. We know how to find it. Okay. And these energies, we know those things. Those are the old unperturbed energies. This is unknown, right? We do not know what these coefficients are. But for sure, we can calculate it, right? This is, this is an algebra 1 equation to solve now for those coefficients. Okay, so let's do it. Okay, so let's consider both the cases where L equals N and L is not equal to N. So if L equals N, let's see, on the left side, we have C, C superscript N, subscript L, times E0L minus E0L. I guess I should write LL there. Whoops, this thing is 0. Ha, that's all 0 over there. Okay, because I have a number minus itself times anything. Okay, so that's 0. And then over here, we have psi 0L, H prime psi 0L plus E1L. Hey, look, this matches what we already found, right? These things are equal because E1L equals psi 0L H prime psi 0L. Look, we already know that. That is the relation for the first order energy, the first order change in the energy eigenvalues. Okay, so that's just a consistency check. That's no new information. Okay, what about if L is not equal to N? Okay, so now we have this relation, let's see, on the left, we have this quantity. On the right, we have this matrix element, and then here's a Kronecker delta term, but we're saying, well, if L is not equal to N, then this thing is 0. So if L is not equal to N, here I can just copy and paste the equation without the Kronecker delta thing. Okay. Here it is. Okay, so to solve for the C and L's, okay, that is just C and L is negative this matrix element psi 0L H prime psi 0N divided by the energy difference E0L minus E0N. Okay, so this is to say we now know these C coefficients. So that's like if we want to solve for an unknown vector, we know the X and Y and Z components of that vector. So that tells us what the vector is, okay? So if we put this into our equation right here, where we do this expansion, okay? I'll copy and paste that one. Oops. All right, so we want to know what is psi 1, okay? So here's our equation. And so now we know all the C coefficients when L is not equal to N. Okay, so what does that give us? Okay, so we have now a sum of all the terms that are not N, okay, and the coefficient that goes here, the coefficient that goes here is this thing that we just derived. So negative psi 0, I'm changing the letter L to M now because I want the subscript M. H prime psi 0N divided by the energy difference, E0M minus E0N, all times psi 0M. Okay, and then there's one more term that needs to be here, and that is the CNN psi 0N. Okay, so we're almost done with figuring out the correction to the wave function. We just need to find one more of those C coefficients, okay? We need to find this remaining guy, okay? The trick to finding that guy is that we need this wave function to be normalized, okay? So we want to say that normalization requires that, you know, the inner product of psi n with psi n equals 1, right, for all n's. this inner product, okay? So that's the inner product of the psi 0n plus the correction, lambda psi 1n. Inner product with psi 0n plus lambda psi 1n. And really, I should say plus dot, 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 plus dot, 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 the higher order things also. Let's work out this inner product as a power series in lambda. Okay, there is a 0th order term, which is psi 0n, inner product with psi 0n. That, of course, is just equal to 1, because the old unperturbed energy eigenstate was normalized. Okay, then what? Then we have terms that are first order in lambda. So plus lambda times, what's first order? Well, we could have the 0th order term here, inner product with the first order term over there. Or we could have the first order term over there, inner product with the 0th order term over there. That's all. Those are the only ways you can get something that's first order. Okay, so that means we have the inner product psi 0n with psi 1n plus psi 1n inner product with psi 0n. And then plus lambda squared times more stuff plus dot, dot, dot. Okay, so again, we want to make the right side equal the left side order by order in lambda, okay? So at 0th order, the 0th order thing on the left side is 1. The 0th order thing on the right side is 1. Check, no problem. At first order, there is no first order term on the left side. That's 0. On the right side, we have this psi 0n, psi 1n, plus psi 1n, psi 0n. Okay, so we can certainly make this to be true by saying let's require that these two functions are perpendicular to each other. That psi 0n and psi 1n have to be perpendicular to each other. Okay. So here is psi 1n. Okay. Let's require that this should be perpendicular to psi 0n. So I will take the inner product of both sides of this with psi 0n. Okay, let me copy and paste that again. Oops, that's not what I meant to do. Okay, so this is psi 1n. Okay, so the inner product of psi 0n with psi 1n, that is this whole sum, and not equal to n, all that stuff in parentheses, psi 0n, psi 0m, plus cnn psi 0n, psi 0n, and all that should be equal to 0. Well, luckily, we know some of these inner products. Right? We know this inner product is 1. And we know this inner product is 0, right? Because in this sum, we have m not equal to n. So that inner product is 0. So this equation just tells us that Cnn equals 0. That term is 0. So all that's left is, well, we get rid of this last term there. Well, get rid of that guy. All that's left is this sum, okay? Conventionally, people get rid of the minus sign and they switch the order of the terms in the denominator, okay? And so our result then is that psi 1n is a sum over the different states of a matrix element psi 0m h prime psi 0n divided by E0n minus E0m times psi 0m. Okay, so this is the result that I've been working towards for the last 45 minutes. All right, so this is then telling us what is the first order change in the wave function. So coming back to our chart of what we're trying to do, that's way back there. Let me see if I can find our chart of what we're trying to do. To find our chart of what we are trying to do, it's right here. Okay. So we want to make a power series for the new perturbed energy and the new perturbed wave function. Okay. So that is the old unperturbed energy, the old unperturbed wave function. Okay. Plus, here's a correction to the energy. We found that yesterday. Here's a correction to the wave function. We just found that now. Okay. Should we keep going? All right. Well, we can keep going just a tiny little bit more. It's actually not that hard to get this guy now. Okay. So let's just do this one. Do one more term, and then we'll stop. Okay. So if we want to get the second order correction to the energy, okay, how do we do it? Well, we want to come back to the set of equations that we are solving. Okay, so you remember we have the time-independent Schrodinger equation, which now is written in powers of lambda. And we have already solved red equals red. We have already solved blue equals blue. What's left? Well, now we want to solve green equals green. Okay, So let's do that. So I want to say these two green terms over here equal these three green terms over there. Okay. And, you know, I will use all the stuff that we have so far to figure out what is the second order change in the energy, which is that thing right there. So let's do it. Okay. So I go to the end here. All right. So I want the green equals green. Well, I'll use a green pen. Okay, so that is lambda squared times the old Hamiltonian H0 acting on the psi 2n plus the perturbation in the Hamiltonian acting on psi 1n, that equals lambda squared times the old energy psi times psi 2n plus the first order change in the energy E1n times psi 1n, the first order change in the wave function, plus the second order change in the energy times psi 0n. Of course, we can cancel our factors of lambda squared. Okay. Now, what I really want to solve for is this factor, the second order change in the energy. Okay, so to do that, let's take the inner product of both sides with psi 0n. Okay, so take the inner product of both sides with the bra psi 0n. Okay, on the left side, that makes psi 0n acting on the old Hamiltonian, acting on this psi 2n. Plus the psi 0n acting on H prime, acting on psi 1n, equals the old energy, E0n, times the inner product, psi 0n, psi 2n, plus E1n, and then the inner product of psi 0n with psi 1n, plus the plus E2n, this thing I really want to calculate, times psi 0n inner product with psi 0n. Okay, so how can we simplify that? Well, first of all, we know some of the inner products. Okay, so right here, we know the inner product of psi 0n with psi 0n. That's 1. It's a normalized state. Right? What about here? we know the inner product of psi 0n with psi 1n, right? That's what we were just working on a minute ago, okay? That is 0, right? This term goes away. Okay, now what about here in the first term? Okay, let's simplify this thing using one of the same tricks that we used yesterday. Okay, that is, we'll let the Hamiltonian act this way because it's Hermitian. Okay, so this is equal to the inner product of the old Hamiltonian on the old wave function, inner product with psi 2n. We know what the old Hamiltonian does to the old wave function. It produces E0n times the old wave function. So then we have E0n times this inner product of psi 0n with psi 2n. Okay. And now this term exactly matches the first term on the right side. So this cancels all of this, okay? So those terms go away. So this tells us then, this equation actually is not that hard, okay? So what we have here is that E2n is equal to the inner product of psi 0n with H prime acting on psi 1n. But we know psi 1n. We just calculated that thing. So let's use it to find what's this change in the energy eigenvalue. Okay, so now E2n is going to be this inner product of psi 0n with H prime and then the stuff that we just calculated. That's all this thing in blue. Okay, whoops, let me copy it, paste it. Okay. Copy. Paste. Oops, it doesn't fit. Oh wait, I don't need this. I can say, let's erase. Now it fits. Perfect. Okay. Wait, I'm seeing something missing in that equation. Did I not copy and paste the last side? There's I didn't copy and paste something. The psi 0m, like that. That cat is there too. Okay, so to simplify all of this, this is the sum over m not equal to n. Let's see, in the numerator, we have psi 0m h prime psi 0n. In the denominator, we have the difference of energies, E0n minus E0m. And then we still have the inner product. It's psi 0n acting on H prime, acting on the ket that's way over here that I almost forgot, which is psi 0n. M. Okay, so now you can see this inner product is just like this inner product, except that what's on the right and the left has been switched. Okay? So you remember that when you switch what's on the right and the left of the inner product, you get the complex conjugate. Okay, so this and this are complex conjugates of each other. So the product is the magnitude squared. So this is a sum, m not equal to n, of the magnitude squared up here. So psi 0 n, h prime, psi 0 m, all that squared, divided by the energy difference. And that's it. And that's as far as I'm willing to go. Okay, so this then tells us the second order change in the energy eigenvalue. Okay, so if we go back to the master plan, which is way back somewhere here. Okay, so if we go back to this plan, we have now calculated this term and this term. Okay. So that's as far as I'm willing to go. That's as far as anybody normally goes. This is where people normally stop this subject, okay? And so that tells us that if we know the perturbation, the change in the Hamiltonian, we can figure out what's the change in the energy eigenvalues up to second order in the perturbation, right? So up to the order of the perturbation squared, okay? 0th order term plus first order plus second order. Okay? And we can also figure out the change in the wave functions, that is the energy eigenstates, 0th order plus first order. And I don't even want to touch this thing of second order, it's just harder. So this is the information that we can extract from the perturbation theory. Okay. Now, the easy term is this one, the first order change in the energy eigenvalues, okay? That's the one that you should really remember, okay? And so, the other equations are a lot messier than that. And you can maybe look them up when you need to use them. But the thing that you really want to remember is this term, because it really is pretty simple. If you want to know what is this change, you just take the old wave function and calculate the expectation value of the perturbation like that. And that's all. Okay, so that's not too hard to do. And so that's the normal thing in perturbation theory that people most commonly would ask you. Okay, let me make a couple more remarks before I wrap up this subject. Okay, so if we go back to our results, like this picture, this equation, for example, you can see that the denominator in here involves a difference of energies, okay, between different states, state number n and state number m. Okay. We have assumed here that those states have different energies, okay? That's what it means when we said at the beginning, when I said at the beginning that we are doing non degenerate perturbation theory. That is, we assume that E0n is not equal to E0m for n not equal to m. Okay. Here's where you can see that that assumption is really important. That, you know, if that assumption were violated, then this term would be dividing by 0, which would be a disaster, right? So then this term, which is supposed to be small, would actually be going to infinity, okay? Horrible, okay? So there are ways to deal with that, which are called degenerate perturbation theory, for how to deal with situations where some of the old states have the same energy, okay? But I'm not going to teach that to you, okay? So that is something else that you can read in the book, or you can learn in a more advanced course, but that's not going to be covered in this course. Okay, so let me talk for the rest of this class about another example of how this enters into atomic physics. Okay, so let's say if we want an example in atomic physics. Okay. We have done a non-relativistic calculation, okay? So we have solved for the hydrogen atom. Without relativity. But, you know, you've learned about relativity in the modern physics class. You might ask, how important is relativity? Okay, so suppose you wanted to figure out that sort of thing. Okay, so one thing that you presumably learned when you were studying modern physics is about the relationship between energy and momentum in relativity, right? So I'm guessing you learned an equation of this form, that E squared is m squared c to the 4th plus p squared c squared, right? Is that sort of familiar from a modern physics class, right? Okay. So this gives us a relationship between energy and momentum, which is a little bit different in relativity than it is in classical non-relativistic physics. Okay, so if we take the square root of both sides, E is this thing, m squared c to the 4th plus p squared c squared, okay? And I will factor out the mc squared, okay, times 1 plus p squared divided by m squared c squared, like that. Okay. And now let's do a Taylor series for this square root. Okay. So if we do a Taylor series for this square root, that's mc squared, and we'll say 1 plus 1/2 of that p squared over, m squared c squared, and then minus 1/8 of p over mc all to the fourth power. And then if I multiply through by the mc squared, this is mc squared plus p squared over 2m, and then correction, minus p to the fourth over 8m cubed c squared. Okay, so in this series, this term is the rest energy, right? The E equals mc squared rest energy of a particle, and it is constant. It doesn't really matter because it's a constant for that kind of a particle. This term is the non-relativistic kinetic energy. That is what we've been working with in our Hamiltonians all semester. Right? Now, if we want to know, is relativity important, we can look at the next term on the list and say, that's a perturbation. And then we can ask, how does that change the energy eigenstates and eigenvalues for the hydrogen atom? That is a calculation that people do in atomic physics, okay? So people say this term is a perturbation on the Hamiltonian, which comes from relativity, okay? And then they put it into perturbation theory, okay? And so they can say, let's use perturbation theory to figure out how does that term enter into the hydrogen atom eigenvalues. Okay. There is a characteristic small number. So a characteristic value of that perturbation which is conventionally called alpha, and it's defined as E squared, the electron charge, divided by 4 pi epsilon naught h bar c. Okay? And numerically, this is a dimensionless number, which is approximately 1 over 137. So for that reason, this 137 is considered to be some important dimensionless number in physics. It tells us how big are the relativistic corrections to atomic physics, okay? And so, you know, some physicists think about this number a lot, okay? And so if you can remember actually setting foot in the science research building back in the days when you could go on campus in person, that the physics conference room in the science research building is room number 137, okay? And so we say, ooh, I'll meet you in room 137, ha, ha, ha. Get it, right? That counts as humor if you're a physics professor, all right? And so we think about that number, okay? And then this thing gives us corrections to the hydrogen atom energies. And people have studied that a lot, okay? And so the Bohr energies, that is the things that we already studied, those things are of order alpha squared times the mass of the electron times c squared, okay? But then there are different kinds of corrections, okay, which get names that people talk about. There's a fine structure of order alpha to the fourth times mc squared. Okay, this comes from things like relativity and from couplings between spin and orbital angular momentum. And then there are even more precise calculations. There's something called the Lamb shift, which is of order alpha to the fifth times mc squared, which comes from a quantization of the electric field. And there is something more that gets the fancy name of the hyperfine structure, which is, it has an extra factor of the mass of the electron divided by the mass of a proton times alpha to the fourth mass of the electron c squared. Okay, and this comes from the interaction of electron and proton magnetic dipole moments. And so for people who want to go into atomic physics with great precision, you know, there's a lot of information available through perturbation theory about all these different corrections to the exactly solvable problem that we have done so far. Okay, with that, I will stop for today. Okay, this covers the principles of perturbation theory. And in the remaining classes on Thursday and Monday, I mainly want to talk about solving some sample problems in perturbation theory and a few other problem-solving practice kinds of things, okay? And so I'm gonna just do some problem-solving examples for you guys and then wrap up with some stuff on Monday also. All right, so you know, I will have some things prepared, but if you have problems that you'd like me to work on, that's fine. You can bring those in also. Okay, I'll stop here and I will see you guys on Thursday.